Electric power transmission is the bulk transfer of electrical energy from generating power plants to electrical substations located near demand centers. Transmission lines, when interconnected with each other, become transmission networks. The combined transmission and distribution network is known as the power grid in North America, or just the grid. In the United Kingdom, the network is known as the national grid. A wide area synchronous grid, also known as an interconnection, in North America, directly connects a large number of generators delivering AC power with the same relative frequency to a large number of consumers. For example, there are 4 major interconnections in North America grid, and 1 large grid for most of continental Europe. The same relative frequency, but almost never the same relative phase as arc power interchange is a function of the phase difference between any 2 nodes in the network, and 0 degrees difference means no power is interchanged. Any phase difference up to 90 degrees is stable by the equal area criteria. Any phase difference above 90 degrees is absolutely unstable. The interchange partners are responsible for maintaining frequency as close to the utility frequency as is practical, and the phase differences between any 2 nodes significantly less than 90 degrees. Should 90 degrees be exceeded, a system separation is executed, and remains separated until the trouble has been corrected. Historically, transmission and distribution lines were owned by the same company, but starting in the 1990s, many countries have liberalized the regulation of the electricity market in ways that have led to the separation of the electricity transmission business from the distribution business system. Most transmission lines are high-voltage 3-phase alternating current. Although single-phase AC is sometimes used in railway electrification systems, high-voltage direct current technology is used for greater efficiency at very long distances, in submarine power cables, and in the interchange of power between grids that are not mutually synchronized. HVDC links are also used to stabilize and control problems in large power distribution networks where sudden new loads or blackouts in one part of a network can otherwise result in synchronization problems and cascading failures. Electricity is transmitted at high voltages to reduce the energy losses in long-distance transmission. Power is usually transmitted through overhead power lines. Underground power transmission has a significantly higher cost and greater operational limitations, but is sometimes used in urban areas or sensitive locations. A key limitation of electric power is that, with minor exceptions, electrical energy cannot be stored, and therefore must be generated as needed. A sophisticated control system is required to ensure electric generation very closely matches the demand. If the demand for power exceeds the supply, generation plant and transmission equipment can shut down, which in the worst case may lead to a major regional blackout, such as occurred in the U.S. Northeast blackout of 1965, 1977, 2003, and other regional blackouts in 1996 and 2011. It is to reduce the risk of such a failure that electric transmission networks are interconnected into regional, national or continent-wide networks, thereby providing multiple redundant alternative routes for power to flow should such equipment failures occur. Much analysis is done by transmission companies to determine the maximum reliable capacity of each line to ensure spare capacity is available should there be any such failure in another part of the network. Overhead transmission. High-voltage overhead conductors are not covered by insulation. The conducting material is nearly always an aluminum alloy, made into several strands and possibly reinforced with steel strands. Copper was sometimes used for overhead transmission, but aluminum is lighter, yields only marginally reduced performance and costs much less. Overhead conductors are a commodity supplied by several companies worldwide. Improved conducting material and shapes are regularly used to allow increased capacity and modernized transmission circuits. Conductor sizes range from 12 square millimeters to 750 square millimeters, with varying resistance and current carrying capacity. Thicker wires would lead to a relatively small increase in capacity due to the skin effect that causes most of the current to flow close to the surface of the wire. Because of this current limitation, multiple parallel cables are used when higher capacity is needed. Bundle conductors are also used at high voltages to reduce energy loss caused by corona discharge. Today, transmission level voltages are usually considered to be 110 kV and above. Lower voltages, such as 66 kV and 33 kV, are usually considered sub-transmission voltages, but are occasionally used on long lines with light loads. Voltages less than 33 kV are usually used for distribution. Voltages above 765 kV are considered extra high voltage and require different designs compared to equipment used at lower voltages. Since overhead transmission wires depend on air for insulation, the design of these lines requires minimum clearances to be observed to maintain safety. Adverse weather conditions, such as high wind and low temperatures, can lead to power outages. Wind speeds as low as 23 knots can permit conductors to encroach operating clearances, resulting in a flashover and loss of supply. Oscillatory motion of the physical line can be termed gallop or flutter depending on the frequency and amplitude of oscillation. Underground transmission. Electric power can also be transmitted by underground power cables instead of overhead power lines. Underground cables take up less right-of-way than overhead lines, have lower visibility, and are less affected by bad weather. However, costs of insulated cable and excavation are much higher than overhead construction. Faults in buried transmission lines take longer to locate and repair. Underground lines are strictly limited by their thermal capacity, which permits less overload or re-rating than overhead lines. Long underground AC cables have significant capacitance, which may reduce their ability to provide useful power to loads beyond 50 miles. Long underground DC cables have no such issue and can run for thousands of miles. History. In the early days of commercial electric power, transmission of electric power at the same voltage as used by lighting and mechanical loads restricted the distance between generating plant and consumers. In 1882, generation was with direct current, which could not easily be increased in voltage for long-distance transmission. Different classes of loads required different voltages, and so used different generators and circuits. Due to this specialization of lines and because transmission was inefficient for low-voltage, high-current circuits, generators needed to be near their loads. It seemed, at the time, that the industry would develop into what is now known as a distributed generation system with large numbers of small generators located near their loads. The transmission of electric power with alternate current became possible after Lucien Gourlard and John Dixon Gibbs built what they called the secondary generator, an early transformer provided with 1-to-1 turn ratio and open magnetic circuit. In 1881, the first long-distance AC line was built for the 1884 International Exhibition of Turin, Italy. It was powered by a 2 kV 130 Hz Siemens and Halske alternator and featured several Gourlard secondary generators with their primary windings connected in series, which fed incandescent lamps. The system proved the feasibility of AC electric power transmission on long distances. A very first operative AC line was put into service in 1885 in Via dei Cerchi, Rome, Italy, for public lighting. It was powered by two Siemens and Halske alternators rated 30 horsepower, 2 kV at 120 Hz and used 200 series connected Gourlard 2 kV, 2OV step-down transformers provided with a closed magnetic circuit, one for each lamp. Few months later it was followed by the first British AC system, which was put into service at the Grosvenor Gallery, London. It also featured Siemens alternators and 2.4-kV 100V step-down transformers, one per user, with shunt-connected primaries. In 1886, in Great Barrington, Massachusetts, a 1 kV alternating current distribution system was installed, featuring both step-up and step-down transformers and resorting also to European technology. At an AIEE meeting on May 16, 1888, Nikola Tesla delivered a lecture entitled A New System of Alternating Current Motors and Transformers, describing the equipment which allowed efficient generation and use of polyphase alternating currents, the transformer, and Tesla's polyphase and single-phase induction motors were essential for a combined AC distribution system for both lighting and machinery. Ownership of the rights to the Tesla patents was a key advantage to the Westinghouse Company in offering a complete alternating current power system for both lighting and power, regarded as one of the most influential electrical innovations. The universal system used transformers to step up voltage from generators to high-voltage transmission lines, and then to step down voltage to local distribution circuits or industrial customers. By a suitable choice of utility frequency, both lighting and motor loads could be served. Rotary converters and later mercury arc valves and other rectifier equipment allowed DC to be provided where needed. Generating stations and loads using different frequencies could be interconnected using rotary converters. By using common generating plants for every type of load, important economies of scale were achieved. Lower overall capital investment was required. Load factor on each plant was increased, allowing for higher efficiency, a lower cost for the consumer, and increased overall use of electric power. The first transmission of three-phase alternating current using high voltage took place in 1891 during the International Electricity Exhibition in Frankfurt. A 15 kV transmission line, approximately 175 km long, connected Laufen on the Neckar and Frankfurt. Voltages used for electric power transmission increased throughout the 20th century. By 1914, 55 transmission systems, each operating at more than 70 kV, were in service. The highest voltage then used was 150 kV. By allowing multiple generating plants to be interconnected over a wide area, electricity production cost was reduced. The most efficient available plants could be used to supply the varying loads during the day. Reliability was improved and capital investment cost was reduced, since standby generating capacity could be shared over many more customers and a wider geographic area. Remote and low-cost sources of energy, such as hydroelectric power or mine-mouth coal, could be exploited to lower energy production cost. The rapid industrialization in the 20th century made electrical transmission lines and grids a critical infrastructure item in most industrialized nations. The interconnection of local generation plants and small distribution networks was greatly spurred by the requirements of World War I, with large electrical generating plants built by governments to provide power to munitions factories. Later these generating plants were connected to supply civil loads through long-distance transmission.